Ladies and gentlemen, I'm Yimano Kojo Kent, a computational nuclear engineer whose research area spans across thermal hydraulic analysis, uncertainty quantification, and sensitivity analysis of research reactors. I'm here to present on our group's project, which is to develop a machine learning surrogate model, an interactive user interface for predicting temperatures and safety ratios for a 10 megawatts material testing reactor under steady state conditions. I meet our team members, myself, and then Ms. Nimatalahi Masood Kahinde, an AI engineer and data scientist with experience in machine learning systems. And then we also have Mr. Asiedu Emmanuel, civil and structural engineer with background in deep learning applications for structural dynamics. One may ask, why are we using 10 megawatts MTR and not any other reactor? And why are we developing a model and then user interface? And why is rapid reactor safety analysis needed? Actually, we had data for the 10 megawatt MTR. That's why that reactor was used. And then we also wanted to develop a model that will be able to predict temperatures and safety ratios without going through the vigorous running of multiple simulations using the thermohydraulic codes. And also to develop or create a user-friendly interface for those that are not nuclear biased. We also wanted to cut down computational costs because high fidelity thermohydraulic codes comes with a cost and is very time consuming. These are objectives that we achieved at the end of our project. First, we identified some key input parameters and their output responses. We then generated thermohydraulic database using our thermohydraulic code, which is the PL temp. We then developed and trained our machine learning surrogate model using the random forest, gradient boosting, and then the neural network algorithms. We then evaluated and then validated our surrogate model. And lastly, we designed an interactive user interface based on the model that we had. So as I already said, the PL temp code was the thermohydraulic code that was used. It's a steady state single phase thermohydraulic code that is used to calculate temperature distribution and safety margins, whether you are using fuel plates or fuel rods. The diagram there is an example of a fuel plate type reactor, as in the 10 megawatts being a fuel plate type reactor. That's why the PL temp code was used. Then we move on to how the project was done, our methodology. We first prepared our input file. And then after that, we generated 1,000 samples using the lighting hypercube sampling technique. And then after that, we ran our simulation using the input file and then the PL temp code to generate our outputs. We then extracted the values of the output parameters that was concerned to us, so that will be needed for the machine learning model. So after training our model, we also developed a Streamlit interface that will be used to predict the thermal temperatures and then the safety ratios rapidly without going through the vigorous activities that I explained earlier on. Here, I'll briefly explain how our data was generated. We have our input file, and then we decided to select some key input parameter, that is the channel thickness, the pressure, power, inlet temperature, and then the mass flow rate. So what we did was to replace the nominal values with characters, and then we wrote a Python script to generate random numbers or figures within a certain range. That will be used to generate the 1,000 samples. So after generating the 1,000 samples, we wrote a driver script in C# that will use the input file to run with the PL temp executables to generate our output file. So as you can see, that's a snippet of our output file. And then since our model wants to predict safety ratios and then thermal temperatures, our output parameters then become the critical heat flux ratio, which is a safety parameter, the onset of nucleate boiling ratio, which is also a safety parameter. And then our temperatures were the fuel and then the cladding temperatures. So we extracted the values for these temperatures, and then we compiled it onto an Excel sheet that will be used to develop our model. We'll then move on to how our model was done and then some of the interesting things that we came up with. My colleague, Ms. Nima, will continue from here. Ms. Nima.
Good evening, good morning, good afternoon, everyone. Can you all hear me? Please, can you confirm that you can hear me, please?
Yes, please. Yes, please.
All right. Thanks so much, Emmanuel. I'll continue from where I stopped. So this part, we had generated a data set containing 1,000 thermal hydraulic simulation samples using the PL type. So before training any machine learning model, the right thing to do is to divide your data set into two, and then you have 80% of your data. We actually use 80% of our data, which is 800 sample, was used for training the model, while the remaining 20%, which is 200 sample, was reserved for testing. So the training set allows the model to learn the relationship between the reactor operating condition and then the safety output, while the testing set is used to evaluate how well the model perform on data they have not even seen before. So now, to identify the best surrogate model, we actually use three machine learning algorithm, which is the random forest, gradient boosting, and neural network, which Emmanuel has explained earlier. And then after training the three model, so the next step was to compare their performance and determine which one was most suitable for our application. Please, next slide. So now, this slide, we have performance results from the three machine learning model. So two evaluation metrics were used. First, the RMSE, we stand for the root mean square error, and it measures the average prediction error. So this is how it works. The lower values indicate better performance, and the second evaluation metric we use is the R squared, also called the coefficient of determination. This actually measures how well the model explain the data. So now, value closer to 1 indicates better performance. So the model were evaluated on 4 output parameters, which we can see here. Now we have CHFR, we stand for critical heat flux ratio, and the OMBR, we stand for onset of nucleate boiling ratio. And we also have our maximum fuel temperature and the maximum cloudy temperature. So now we have the random forest, which achieve very strong results across all outputs. However, we have the gradient boosting, which achieve even higher R square value and a lower RMSE value for every output parameter, which we can see here on this slide. So this means it produces more accurate prediction with smaller error. And then we also use the neural network, which perform poorly, and it produces negative R square value. So this indicates that a negative R square indicates that the model performed worse than simply predicting the average value. So based on this result that we have, gradient boosting was selected as the final surrogate model because it consistently delivered the highest predictive accuracy that we want to use. Now, this table that we have here provides the numerical results. And please, next slide. In my next slide, I'll present the same comparison virtually. So now we can see that we can see the virtual comparison of the three machine learning model that I've explained earlier. And the chart on the left displays the R-square value, and it has higher value indicates that better performance. And we can see that both random forest and gradient boosting achieve values very close to 1. And then this indicates excellent predictive capability. However, if we can notice, gradient boosting consistently achieve the highest value across all the outputs. So now the neural network performed poorly and it produced a negative value. And the chart on the right displays the RMSE value, and it has a lower value, indicates smaller prediction error. So once again, gradient boosting achieved the lowest error across all output parameters. And then this result clearly shows that gradient boosting is the most accurate and reliable model among the three algorithms evaluated. So in my next slide, I would and before that, after we selected the gradient boosting as the best performing model, we then validate its prediction against the original PL temp simulation result that we had. Please, next slide. So we compare the prediction generated by the gradient boosting model with the actual output from the PL temp simulation. So each scatter plot, oh sorry, not this slide. Slide 11, please. Can you hear me, please? Yes. No, back, please. Can you go back to, okay, yes, thank you. So now, in this slide, we compare the prediction generated by the gradient boosting model with the actual output from the PL term simulation. So each scatter plot represents one output parameter. So for every point corresponds to one sample from the test data, the horizontal axis shows the actual simulation value, while the vertical axis shows the value predicted by the machine learning model. The dashed diagonal line represents the perfect agreement between the predicted and the actual value. So therefore, the closer the points are to this line, the more accurate the model is. So across all the 4 output parameters that we are seeing here, the plot cluster very closely around each perfect prediction line. And so this helps to demonstrate a very strong agreement between the machine learning prediction and the thermal hydraulic simulation results. So after confirming that the model was highly accurate, we performed a sensitivity analysis to identify which input parameters had the greatest influence on the prediction. Thank you. So we have the sensitivity analysis. So the purpose of doing this was to determine which input parameter have the greatest impact on the predicted output. Each row represents an output parameter, and then each column represents an input parameter. The color intensity represents the level of influence, and the darker color indicates a stronger influence on the prediction. So there is a clear pattern that we can observe here. So mass flow rate is the dominant parameter across all 4 outputs, and it contributes approximately 95.8% of the influence on the CHFR and 97.3% for the OMBR, and about 99.6% for both the maximum fuel temperature and the maximum cloudy temperature. Now, the fact that the machine learning model identifying this relationship from the data gives us additional confidence that it learns the underlying reactor behavior correctly. And I'll give to my next colleague to continue from where I stopped. Thank you.
I want you to know you have 1 more minute. Okay. Good evening, everyone. Good afternoon, good morning. So mine is to present on the interactive user interface. So I've placed the link to the app, the web app, in the comments in the section, the chat section. So you can check it out. So Mensa, can you play the video? Let me use it to the demo on the presentation. So we integrated the model, the best model we had, into this web-based application. We use Streamlight to do it. So from the presentation, you can see that we have the predictor part. So when the video gets to that, so yeah, we have our input parameters here. When you input the parameters into the input parameters and you click on the predict, you get the output parameters, and it also predicts whether the output parameters are safe enough for you. So this is what we did for the user interface. It provides accessibility, like it improved accessibility. The interface enables users to perform the thermal safety assessment without running computationally expensive simulations. So let's go to the next slide. That's the conclusion. The next slide. Okay, there's a discussion. So my colleagues have already mentioned most of these things. We developed a surrogate model for this, and the gradient boosting was the best performance, and the user interface also reduces the prediction time, because for this, you are not going to run any computational stimulations. The user interface, since it's integrated the best model, or we integrated the PKL file into the user interface, so it makes the prediction easy. And we also found out that the mass flow rate had the highest influence through the sensitivity analysis. Please, the next slide. So from this, so it's part of the findings we had and also the conclusion we had. We did the gradient boosting achieved the highest prediction accuracy. The ML prediction closely matched the simulation result here. And the framework also improved the accessibility of reactor safety. Next slide. Yeah, so this is our future work, or any future work that can be done to it, the transient model. We have to extend this to predict the surrogate model to predict reactor response under accident conditions. These are dynamic conditions, but what we did was actually on steady state conditions. And the multi-phases coupling, we have to integrate neural kinetics, full performance, and also structural mechanics to fully coupled multi-phases surrogate. And the digital twin, since this is already an ML-based prediction, and we also have a user interface, it will help us get real-time predictions. And when real-time, real-world or real-time predictions, yes, please. Then we go to the last section. So those are the acknowledgements. So at this point, we want to thank the Center for CCRE for providing the facilitation team, Dr. Brian, Dr. Titus, James, for what he has done for us, guiding us throughout this project and everything. We also want to thank Engineer Professor Joseph Opon Akoa for helping the team to putting up this project or this training as well. We also want to thank the Boa State University for providing access to this cluster and also resources, and also we want to thank them for the office hours they provided to us. So I think this is the end of our presentation, and thank you, everyone.
I am Prince Kofi Siedu, and I'm a member of Group 2, and we'll be presenting today on Neuroscan, our brain tumor classification from MRI scans using transfer learning. Next slide. Brain tumors are a life-threatening situation that pose severe risk to health of human beings. Diagnosing brain tumors is a time-sensitive activity in which untimeliness or not being timely then causes the situation to further escalate beyond repair. And beyond repair. Manual MRI is very slow and subjective to the individual. It's also prone to inter-reader variability, where we are saying that different people can come with different readings based on their experiences and other factors. In sub-Saharan Africa, there's a severe shortage of radiologists, people who can do this MRI review. In sub-Saharan Africa, they are as low. There is the ratio of radiologists to patients is as low as 1:8.8 million, as opposed to the situation in Europe, where it's 13:100,000. However, with the advent of AI, we are seeing a situation where we can have AI-assisted classifications to augment this decision-making process. Next slide. Currently, AI studies are able to AI studies done in this field have benchmarked single architectures. There are no systematic comparisons of different architectures and how they are performing and how to use them in real product situations. There are very few open source reproducible models for low resource African settings. And this gap is a situation we aim to bridge. Next slide. We aim to develop, with this project, we aim to develop an ensemble of the CNN transfer learning models for robust automated brain tumor classification. And to do this, we are pre-processing brain tumor data sets with skull stripping, resizing, and image net normalization. We then fine-tune EfficientNet B3, which are the models we selected, EfficientNet B3, VGG16, and a DenseNet 1-to-1 via a two-phase transfer learning process. We then evaluate each model individually on 4 evaluation methods: 1, accuracy, precision, recall, and weighted F1, identifying per-class weaknesses across all these architectures. We then combine these 3 models to form an ensemble through the soft fault ensemble method, averaging class probability so that errors specific to individual models can be suppressed by an agreement by other models. We are then deploying this ensemble model via web application to make it available to the average person or hospital.
Yeah, so continue, I'm blessed. To continue to talk about the 3 architectures we went with. For our models or the architecture, we chose 3 main architectures after replacing 1 out of 4 initially. Then with our VGG16, which is one of the most cited baseline medical imaging architectures. So we use that as a baseline to compare the performance of the other 2 to see if they would perform relatively better comparing to something that is being used in most academic medical papers. So we went with the EfficientNet B3, which is known for balancing fine detail and broad spatial context. And then the DenseNet 1-to-1, which uses about 17 layers. And then one of its features, it allows for fine detail detection and then doesn't get diluted easily. And then along the way, we had to add focal loss to the DenseNet to cover up for misclassification between the 2 main classes, which is the glioma and then the meningioma. And then we added a custom 4-class classification head to the backbone of each model. Since we already had a pre-trained, we're starting with a pre-trained model, ImageNet. So for our data set, we went with 7,200 scans, image scans, grouped in 4 classes with 1,400 images per class for training, and then 400 per class for test. The test set is held out completely during the training. And then we went with this data set because it's one of the most cited data sets on Kaggle, voted for its use, and then it's conformed with its clinical usefulness, meaning it was already classified in the 4 main classes that we classify tumors, and it was not just a no tumor and tumor class data set. For our setup, we went with a few pre-processing stages with 4 main ones listed here. The first was an RGB conversion, which is to convert our MRI scans from a single channel grayscale image to a three input channel for our pre-trained backbones. And then we had to resize to a uniform for uniformity across all three models, which we chose 224 by 224, which was favorable to, which was the default size of the two models, VGG60 and DenseNet. And although efficient Net 3 works best with 300 by 300, it could also work with this. And then after that, we converted our field images from integer pixels to floating tensor points, and then we normalize this to reduce the variance in our inputs. And also to make the data set more robust, we did some augmentation, which involved rotation of the images, and then we did some vertical and horizontal flips and kept those as additional dataset images to make our dataset more robust. So for our architecture, we had a two-phase transfer learning pipeline, and then we started with a pre-trained CNN backbone frozen, which was for the phase 1, and then we continued with an unfrozen backbone to allow for all to train during the fine-tuning. And then we adopted the Adam W plus cosine annealing LR, which gives millions of weight to its adaptive step size. And then the cosine annealing smoothly decays the learning rates within each phase, so training is aggressive and early, without manual scheduling loops. For during training, since we're struggling with the glioma and meningioma differentiation, we added focal loss on the DenseNet 121 to allow for standard cross entropy traits. And then this, so after the phase 1, we saw that there was good performance with the no tumor and then the pituitary. So adding the focal loss increases so it downweights the already performing classes and then gives more priority to the class with very low confidence, which was the glioma. So this is the graph showing the training phase. And then as you can see here, we have for each model, which we have the AB, efficient net 3, VG16, and then the dense net 2. We have the first one showing the loss, training loss, and then the validation, and then the efficient, the accuracy at the right side. Then you can see the curves going down for the loss. We have the phase 1 seeing a significant drop, and then we have fine tuning, which was done, and we got about 5 to 10% in decrease in the loss, and then about 5 to 10% increase in accuracy across all 3 models. Hello, Prince.
For our results, we evaluated our models with 4 evaluation methods, as stated earlier, which are accuracy, weighted F1, weighted precision, and weighted recall. From the graphs, you can see that our models, can you see my mouse pointer? Okay, I don't think so.
No, but if you can, yeah, so you can continue. I'll try my best to.
From the graphs, you can see our models performing fairly high with a minimum of 91% accuracy and 91.3%, 91.9% weighted precision and 91.5% weighted recall. What this means is that our models are very good at, well, our models perform fairly well when it came to identifying each class, right? Meningioma, pituitary, no tumor, and glioma, right? And on to our right, we have the per class recall where we see our model, where we see the breakdown of how each model works with each classification. So We have a consistent 96% recall across all models. And for our most challenging class, the glioma, we have 77.8 on efficient-net B3 and 80.8 on the dense-net 121, which is where we did we added the focal loss to improve its recall and ability. The next slide. So from this, we see that all our three models exceed 91% in accuracy. VGG16 was our best model, which has very good meningioma recall, which is very important because meningioma is often benign, right? And being able to detect this situation and prevent this from further expanding in the person is the difference between life and death. DenseNet 121, which is also one of our best models for one of the difficult cases in tumor detection, which is glioma. It was also developed. We have Grad-CAM heat maps, which are able to help us or help both us and the radiologists confirm the output of the models. The reason why we included this is to build trust with our radiologists who are able to confirm the output of each model. There are a few limitations, one of which was having a single data set for this study, where we also did not have any external validation. We did not include any external radiologists on the system, in the development of the system. We also have a class distribution which differs from the real world situation. In the real world, we have more no tumor situations than the others. But in our training, we had a consistent number of cases for each situation, which does not reflect what actually happens in the real world. Next slide. So this is a demo of the application that we developed to be able to classify brain tumors with AI. So you have a landing page that explains what is happening on the system, how it works, the different kinds of models, and a call to action that allows people to begin. You're able to drop an image into the system and select a model for which we will now receive a prediction. So we will see that happening, and then you have an analyze scan. So after running inference, which can take about 15 to 60 seconds, you have output, which tells you what classification, what type of tumor you have, and the reason why it thinks you have that tumor, in this case with a Grad-CAM heat map, like we discussed earlier. It also tells you its confidence score and class probabilities for the other cases or other classification cases. Next slide. We spoke about a few limitations, but we aim to work on these in the next steps of this project. One of which is the use of segmented data, which in a real world situation, you'd have radiologists look at the scan data set and assess areas that are the model should actually pay attention to before we even do training. So we didn't do that in our pre-training step, and that's one of the things we'd like to do to improve our model. We also like to have external validation. What that means is to be able to consult, have radiologists actually on board from the beginning to the end of the entire process, and also to validate our model at the end of the day. We also would like to have a multimodal infusion of MRI with clinical data. Our study focused on only scans, but a way we can improve the model is to have more information about the patient included in the training, where you have demographic information, situations relating to maybe Blacks might be different from what happens to other people in other continents. So we like to have that as part of the classification. Next slide. We'd like to acknowledge Masood Nikpava, whose data we used for this study. We'd like to thank our instructors, the organizers of this program, Dr. Titus, Dr. Brian, Kianju, James, Doreen. We'd like to thank Engineer Professor Joseph Opon Akua from the University Department of Agriculture and Biosystems Engineering. And last but not the least, Boise State University for providing HPC, which we use for the study. Next slide. This team comprises of Bless Elikem, Kappa, myself, Prince Kofi Esiedu, and Uranius, people of different backgrounds that came together to make this a reality. And this work was completed as part of the CCRE HPC Research Training Program. Once again, my name is Prince Esiedu, and thank you.